welcome. This is the session about garbage collection, and particular in one garbage collector algorithm that we are developing at Red Hat. So this talk is pretty dense content-wise, so I'll try to speak fast. If that's a problem, don't be alarmed. If you lose the thread, just wait until the next session. Until the next section, and it will be all right after that, again, for some time. All right, so safe harbor. This is the only slide in partly Russian. Learn Russian while it's still voluntary. It's basically said that whatever I say here might be a lie, so if you try to depend on this in your production systems, then please hire the professionals that will tell you what exactly is wrong with these slides. Okay? And the second thought is that this talk is interesting in itself, but if you want to have deeper understanding about GCs, you have to read this book. It may appear in any other GC talk that what is being explained is something very innovative and everything is rewritten from scratch, etc., but in reality, most of the GCs reuse the ideas from this book, Shenandoah included. So there's that. Overview. Why in the hell do we need another GC? How many GCs are out there in OpenJDK and Oracle JDK? 4. Okay. So if we try to look at them, we will start with something simple like serial and parallel GCs. Those GCs are generational. They are schematically can be described like this. Young collection is the copying collection. Old collection is mark and compact. They are orange on these slides to signify that they are happening during stop the world, meaning that the entire GC is stop the world regardless of if it's young or old. So if I want to do some parts concurrently, what collector do I use? CMS. CMS does all GC concurrently. It has concurrent mark and concurrent sweep, but the concurrent in the concurrent mark sweep only relates to the old GC. The young GC is still pretty much copying stop the world collector. And the trouble with concurrent sweep is that it keeps the object in place, which means eventually you will fragment the old generation, which you will have to deal with. Most people deal it with tuning, try not to promote as much, or do some other magic. If CMS does not fit the bill, what do I do? J1. J1 on this picture looks like a step back because it has more orange parts. The green parts are concurrent parts. But the virtue of J1 is that that collector is regionalized, so it can control the poses by selecting carefully how many regions you would collect. So even though it does concurrent mark and stop the world compact, the duration of that compact is adjustable. And it still does young GCs pretty much like any other collector in OpenJDK. Shenandoah on this picture looks like this. It does most things concurrently. It does concurrent compact, which means which combines kind of the best of two worlds. It's concurrent like CMS and does compact like J1. Why don't other GCs do that? I hope it will be clear after this talk. So before we go into the deep dive into what Shenandoah is, let's do the first basic thing. Shenandoah is the regionalized GC. If you are familiar with J1, you will find many similarities between the two. The heap division, the handling of humongous regions is similar to J1. It also collects the garbage first region first. In contrast to J1, it's not generational by default. There is no young and old separation, even temporarily, in the default mode, etc. If we would like to look at the GC cycle that happens in Shenandoah, it does 3 major phases, and they go like this. So suppose you have the application and it allocates something in the heap. The blue things are what applications had allocated. And at some point, GC decides that the memory is running out, and it's time to do the GC. So the first major phase in the GC cycle is concurrent mark. And concurrent mark has 2 poses, before and after it. We will talk about why. But at the end of concurrent mark, we know which regions contain alive objects and how much. So those greenish progress bars are roughly the depiction of how many objects are alive there. So after the mark, we can actually say what regions are the targets for the collection. We can mark these regions with this yellowish bars there, say that these regions form so-called collection set, the set that we are collecting right now. And the second phase comes in, which is concurrent evacuation, which takes this collection set and evacuates all the live things from there into a new region, thus compacting it. After this stage is over, you might think that GC is over, but no, you have also to update all the heap references to the object that you have moved to not to point to the collection set anymore, but rather to the new object locations. And that phase is also concurrent. It has two smaller pauses as well. And if you run a usual Java application after that, you will recycle the collection set. You can allocate there. If you run it, the usual Java app, 100 gigabyte heap. My desktop has that much memory, so I can do it. And you put 80 gigabytes of live data in this heap, and this is the GC log that you will have, and these are the pauses. The pauses are still there. It's not completely concurrent, but the pauses themselves are very, very small compared to the length of the concurrent phases. So sub-millisecond pauses, anyone in Java who is in for that? Woo! Yes. Now we will tell what it costs us, right? So to understand that, we have to understand how GCs work. And to understand how Shenandoah works, it's important to understand how, say, stop-the-world collectors work. So the first thing, before you do any GC, you have to figure out what is garbage. And to figure out what is garbage, you have to know whether there are references to the object. And there are three basic approaches there. First, very basic, ignore the problem and say that everything is reachable. If you know what epsilon GC is, it's what it does. It says we don't collect at all. Everything is reachable at all times. We can do mark and something. We can say that, we know this is the set of implicitly reachable objects. You know what those objects are, right? For example, static fields, stacks, etc. And treat everything else as garbage after we marked everything alive. And reference counting. When we say, we will get a counter attached to each object, and when that counter goes to 0, that means no references to the object, and we can treat it as garbage. If you look at this, you can actually think that reference counting is actually more of the GC than mark, because it identifies the garbage directly. And the mark is does that by exclusion. So whenever anyone says that reference counting is not the GC algorithm, well, it's more than garbage collection algorithm than mark. Okay, so let's dive into the mark. Turns out we can do this walk through the graph if we assign colors to the object. And Dijkstra assigned 3 colors, come up with the 3-color abstraction. You have to be pretty depressed person, I think, if you are asked to choose 3 colors for coloring and you chose white, black, and gray. But here is the classical arrangement. White objects are the objects that we have not yet visited. Black objects is the objects that we have visited, and all the outbound references are scanned, and gray is something in the middle. So in other words, concurrent mark is the thing that turns white into gray and gray into black. So let's do the example to see how it works. So we have the stop the world mark, and we have this object graph, and the white circles are the objects, and we have the root set, which is the black square, which is implicitly reachable, and in the pointers are the references between those objects. When the application is stopped, everything is perfect. We just scan from the root set, color it black. Everything reachable from black is gray. Now everything gray is black, gray, black, and this wave sweeps through the graph and marks everything reachable, marks everything black. All garbage is white, and we can recycle it, period. The GC is completed. When you do the concurrent mark, you get problems, because applications not only write to the heap, but they actually actively mutate the reachability graph within the heap. For this, some textbooks call applications mutators from the standpoint of GC. So how does it get problematic if we come to the same example, but now we assume that application does something? So we have arrived to this second gray objects there, and we were trying to scan the link to the right from that, but at the same time, application destroyed the link to the white object there. And if it just destroyed it, we would be fine. It would be garbage then, but it could also insert the reference to that white object to some black object that we will not visit anymore because the wavefront kind of moved on from that. And there is another case which is subtly different, but you can think about it the same. You can also destroy the reference to the white object and insert it into some, and insert the reference to some transitively reachable white object into the black object. So if you complete the mark in this case, you will realize that there are two objects which are now reachable, but your marking algorithm says they are white. You're just reclaiming their space and thus corrupting the heap. There are two classical ways to deal with this. Some of them are tracking assertions, some of them are tracking destructions, and J1 and Shenandoah does the algorithm that is called SayTB, which works like this, which says, okay, we know that destructive writes are bad, so why don't we track them? So on every write, we try to see if we have destroyed the link to the particular part of the graph that we might have to walk. We just record it. In this abstraction, we just mark those objects gray and continue the scan from there. And also, if you have new objects, we can also color them black or gray, depending on the algorithm, and thus complete the mark, even though the new pointers are there. So if you compare this graph with the graph that you had under Stop the World mark, you will notice an odd thing, that this graph is actually the superset of the graph that you had in the Stop the World. So you have marked everything that was reachable at the start of the collection, because everything untouched you just walked through. Any destructive write that happened during the mark, you walked it anyway because SayTB did it for you. And this is why SayTB is called SayTB. It's the algorithm that is called snapshot at the beginning. And it marks everything reachable at mark start. The troubles with this, of course, is that it overestimates liveness. Everything that you have allocated during concurrent mark is implicitly alive. Any destructions that happen during concurrent mark are still treated by GC as effective. But what does it mean to intercept writes? That means the runtime should insert some instructions around the actual heap writes to intercept that. And those blocks of code are usually called barriers, to greater confusion because these are GC barriers, not the memory ordering barriers. So for SayTB, the barrier is called SayTB barrier, and as far as most high-performance things go, they usually have the fast path, the optimistic path, and the slow path, the pessimistic path. So the fast path for SayTB barrier says basically this: if we have the store in the heap, on the off chance it is a destructive store, we have to check if we are during concurrent mark. If we are, then we jump to the slow path. If we are not, we just follow through. And the slow path looks like this. It would be very dumb to go to runtime on every single heap write. The overheads would be too high. And this is why every thread has a buffer where it stores the addresses that are coming from the SayTB buffer. And when this buffer overfills, it just puts the whole buffer to the VM to process. And from this logic, you understand why there are two poses in concurrent mark. First of all, those poses are needed to resolve the races against the mutator. It would be very sad to arm the SayTB barriers and then realize that the application had already passed through that barriers and did the destructive write. Also, you want to probably color the root suit black, but this is not a requirement. You have to arm the SayTB barriers. For the final mark, you want to drain those SayTB buffers now, because threads might have lingering buffers there. and finish work from that, because you might have white objects in those CTB things that you have to process. And so these two things are the most heavyweight parts in the pose. If you look at that, you will realize that the poses are not actually dependent on the heap size. Rather, they are mostly dependent on the root set size and the, you would call the how active the application is, even though it's rarely a problem. So if we have the CTB barrier now, which before every single reference store, what do you think the performance overhead of the CTB barrier is? Who is for 10% throughput? 20%, 40, 5, 1, 0. If you look at the workloads, if you have the suite of benchmarks, you will realize that even the fast path of CTB, which has like 3 instructions before each store, costs you. So you can have the overheads of around 3% just because of the CTB. And this drives us to the first observation, that throughput-wise, a well-engineered stop-the-world GC would beat the well-engineered concurrent GC because there are these barriers there. If you have the budget of 10% throughput overhead for your concurrent GC and you already spent 3% on the fast path for CTB, you have already lost. You haven't started doing anything. You're already off to the races. And the second thing, that the barrier costs are visible even if there's no GC cycles happening. So if your GC log is empty, it doesn't mean your GC overhead is 0, because the barriers are still there. So concurrent mark is easy enough. G1 does it, CMS does it, Shenandoah does it. Concurrent copy is not so much. To understand what's the problem with the concurrent copy, let's first see what is the stop the world version of the copy. So suppose you have the object. It has the header, it has 3 fields, it has references from somewhere from in the heap, and we need to move it to the new location. Stop the world does the simple thing. It says, we stop the application so that it could not mutate or observe any transient state. So then we do the copy of the object. Then we store the reference to the new object somewhere in the old object so that we know how they are connected. And then we walk through the heap. We discover the reference that points to the alt copy. We know through the forwarding pointer where the actual copy is. We gradually rewrite all the references to the new object. At that point, old object is not needed. Stop the world can be relieved, and we are done. With concurrent copy, it gets interesting because application is now writing into the objects that we are trying to copy. So what do you do then? Before you understand what to do then, let's see the failure scenario, what could go wrong. And the problem is, while object is being moved, there are 2 copies of the same logical object, and both of these copies are reachable, which means that the first thread could write in one field of the other one copy, and another thread could write into the field of the other copy. So suppose this happened. So which copy do you think is correct? Who is for the left one? It's a legit thread. It did all legitimately. Who is for the right copy? Who is for both? Of course, and JMM is kind of hard on us here. It does not allow us to lose writes. So both of these copies are correct, and now you're faced with the weird problem of merging them. And hopefully you will do that without violating JMM, which is another problem in itself. And if you look at this, you will understand that the problem is that those copies are of the same rank. There is no way to distinguish which one of those copies is actual. And there is no central knowledge or central location which can tell you which copy is actual. And basically, this is the problem of object versioning. And to understand how Shenandoah works, it's important to understand how would you solve the same problem in Java. If you have the Java object that is mutated by multiple threads, and you want to have the lock-free updates there, he'll probably do something like this. He will do the atomic reference, and then if you want to write to that object, you will do, get the alt copy, get the alt object, do the copy of it, update the copy, and try to install this new copy as the actual version. And that atomic reference would act as the arbiter that will always point to the most actual copy of the object. Who wrote this code at least once? Yeah, I mean, it's the usual pattern in the concurrent programming there. So from there, it's natural to apply the same principle to GC, and that's what Brooks did. It said, OK, why don't we provide the atomicity of object version change by additional indirection? Instead of doing separate object, we just attach a forwarding pointer at every object at all times, and it will tell us where the actual copy of the object lies. So when we have that, it's very easy to construct the copying code. So on first step, we just copy the object, initialize the forwarding pointer to itself. And at that point, we have the copy of the object, but nobody knows about that copy anymore yet. No thread could write into it. It's just our local copy. And then we do the compare and set on the forwarding pointer, thus installing the new version of this object. And this is the major trick that gives us the lock-free and race-free evacuation of the objects. After we did that, we can just gradually rewrite the references to the rest of the heap. And even if the thread comes and tries to write to the object, by construction, it has to do reference through the forwarding pointer first to discover the actual copy of the object and write there. And that's about it. After all the references have been updated, the from space copy is not needed anymore. We can recycle it. And there we go. We have managed to move the object while the concurrent writes happen to it without races. So how do you enforce that invariant? Of course, if you want to enforce this two-space invariant that writes are only happening to the actual copy, you need the write barrier that intercepts the writes and the references through the forwarding pointer. But it might be more complicated than that. So for fast path, the write barrier looks similar to the SATB barrier, right? It checks that if we are, if at this interesting GC phase when we are about to evacuate the objects, that then we jump into the slow path. If we are not, we just do the store, and we are good. So that slow path, I wouldn't bother you with assembly. It's kind of hard. So pseudocode instead. It's eerily similar to what you will do in Java and what we did in Java example. We say that if you want to write value to object at a particular offset, we just say, OK, before we do that, let's check that we are in the needed configuration. So evacuation is enabled, and we are in this GC phase. The object that we are trying to write to is in the to space, and it's not have been yet copied. So that means that the forwarding pointer still points to itself. If we trying to write to that object, that means we have to evacuate it first, because we can only write to the actual two-space copy. So how do we do that? The same way we will do this in Java. We copy the object, we update the copy, and try to install it. The simplification here is that if we have failed this cast, that means someone else had managed to evacuate the object before us, and all we need to do is dereference through the forwarding pointer, discover the actual copy, and write there. And it's by definition would be in the to space. GC evacuation code is similar like that, but it doesn't have to write into the fields now. So it only goes linearly through the heap and says, if the object is in the collection set, is the regions that are destined for evacuation, and it's not have been yet copied, so the forwarding pointer still points to myself, I copy and try to install it. If my cast fails there, we don't care, because that means that the application's write barrier had already copied this thing. And it nicely terminates because there is the finite number of objects in the collection set, so we will reach up the end of the algorithm there. So what do you think the overhead of these write barriers on the applications are? Who is for 20%? 10%. 5, 3, 1. There's no overhead. No? No takers. Huh. OK. So on the real-world applications, there are overheads not that much. On some applications, there are overheads up to 10%, but those are very pathological cases. In most of the cases, you manage to get the overhead quite low because the fast path is really fast. So the observations. Shenandoah needs write barriers on all the stores. If you store the integer into the object, you still might need to copy the object out of the collection set before doing so. If you do metadata manipulation on the object, say you are locking on the object, you have to do write barrier and do the locking on the two-space copy. If you compute identity hash code and thus modify the header of the object, it's still a store. You have to do the write barrier. But the filters that you do on the write barriers are pretty much effective. So we have estimated that 1 in a million, I guess, write barriers actually hit the Slowpath in the real applications. The flip side of this story is read barriers. Now you want your applications to read from the actual copy, or do you actually? It's not a strong invariant. Memory model, by the way, allows you in some cases read from the stale copy, and so you can play tricks on that. But to do this, before each read, you have to reference through the forwarding pointer, right, to get the actual copy there. And so read barrier looks like this. If you have the heap read that reads at the given offset, you just do the reference through the forwarding pointer, and it does cost you a bit. It's just a single instruction, but it does. So if you just run this simple benchmark that does nothing but reading from the heap, and on all paths you have accumulated 3 read barriers, you will have an additional L1 load, and on most hardware it will be pretty well executed, so you will waste a single cycle per read barrier and a single instruction there. So what do you think the overhead on the real applications of these read barriers are? Who is for 30%? 20, 10, 5, 3. Come on, it's a simple instruction. 1. All right. It goes like this. And the observation that you can get from these things and looking at the workloads is that read barriers are cheap, but there are lots of them. And this is why any GC that makes read barriers heavier, say by employing colored pointers or something like that, is probably running into the problems, performance problems there. You cannot make read barriers much heavier because you will make your application go slower. And the observed overhead really, really depends on how well you're able to optimize the barriers there. For instance, how well you're able to pull out the read barriers after the hot loops, for instance. If you don't, you're going to have a bad time. So if you're doing high-performance GC, you have to assume that you will be doing the high-performance compiler work as well. Around 1/3 of our patch against upstream, I guess, is the compiler optimizations. All right. Shenandoah-specific trouble. Now that we have 2 copies of the same object, how does the reference equality work? The machines, the JVMs right now, they just say, okay, if user wants to compare ACMP, reference comparison between 2 references, we just compare the machine pointers. But for Shenandoah, it's not true anymore, because in some cases, machine pointers are not equal, because they're pointing to the different copies of the same object, which means that you have to do additional things to make it work right. And if you analyze this, you'll realize that if you compare the machine pointers and those pointers are not equal, that means the objects are not equal and you're done. If the pointers are not equal, there are cases. It could be a false positive. It could be the from copy and to copy of the same object. So the easiest way to deal with that is just perform the read barriers on both operands, which will inevitably point to the single space and compare again. What do you think is the overhead of this thing on the real applications? 20%, 10, 5, 3, 2. All right. Turns out only a few applications actually get hit on that, but when they do, you have the performance throughput overhead. And the observation from that is that full-fledged comparisons are rare. In Java, you are mostly comparing with what? With null. You're mostly comparing with null. In this particular case, read barrier is not needed. If the pointer does not equal null, that regardless of what copy of object I'm referencing, it's still true. And there's also a problem with the reference classes, which also kind of do reference comparison, but the barriers there is much more complicated than just simple ACMP. The saving grace there is that when you hit the concurrent set Slowpath, when concurrent set fails, you usually have larger problems than the GC barrier. You have to retry, you have to allocate something, it goes there. So in total, if you just count the barriers overhead, the throughput overhead for such a collector would be in the realm of 1 to 20%. And that's the cost that you pay for diminished pauses. But the observations about this is this scheme does not really require anything special from the hardware or the operation system. It's pure software. You don't need kernel patches for it to work right. You don't need special kernels. You don't need special operation systems or special hardware. It just works. And the throughput hit, what our adopters are reporting, is mostly acceptable for them because they are trading the latency for it. And this is the latency throughput trade-off again. If you don't need low latency, don't bother and use stop the world or semi-concurrent GC, you will get better throughput out of it. By show of hands, who knows about generational hypothesis? All right, not that much. So there are two types of generational hypothesis. First is the weak hypothesis, which says that most objects die young. If you draw it, and the x-axis is age, and the y-axis is dying probability, it will probably go like this. This hypothesis is true in many, many languages, not only Java, basically in the most languages out there. And there's this stronger variant of this. It says that the older the object, the less chance it has to die. It's stronger because it's more encompassing. It includes the weak generational hypothesis in itself. Do you know the counterexamples for the strong hypothesis? Can you guess? Can you guess the workload that does not fit the strong hypothesis? Caching. In memory, say LRU-like caches are prime counterexample of this. They will have the occupancy like this. There would be some amount of child mortality in these objects, but it will also dereference the oldest objects there. And this is a very inconvenient workload for the simple generational GCs, because once your cache is not full and it starts to full, it works as the weekly generational workload, because some objects die young, indeed, some of the temporaries. The objects that have promoted are just kept referenced by cache. Everything is fine. But then cache gets full, and because it's a cache, it has the multi-gigabyte live data set there. It starts to reclaim the objects that were there the oldest, probably. Thus, it suddenly stopped being, generational workload there. So how do you do the simplest LRU implementation in Java? Just for the giggles, how do we test the GC? Heinz knows this answer. Yeah, you basically have linked hash map and say, there is a protected method which says, should I remove my eldest entry? And you just say, if you're too fat, then do it. And this is the simplest LRU implementation in Java. If we do that test and we do the very boring config, we do Shenandoah GC, Shenandoah JDK 10 forest, we do a simple desktop with the 100 gigabytes of RAM, and we have the decent hit rate on the cache, and we try to drag through the cache some amount of data, say a terabyte of data. And we want to vary a free variable in that experiment. And the natural free variable in this experiment is the size of the cache, which roughly correlates with the size of live data that you have in the heap. And by varying this lever, you can actually expose interesting GC behaviors there. So if you do this experiment, you will have something like this. The yellow lines are kind of the distributions. It should be violent plots, but the graph would be very, very messy. And the black dot is the average. Even though average is the bad composite metric for this, it still has some meaning here. Notice that the y-axis is logarithmic, which means that the line here is the second, 10 milliseconds, 100 milliseconds, 10 milliseconds, etc. And you might notice that Shenandoah is there in the sub-millisecond range. CMS is somewhere in the middle between parallel and Shenandoah, and G1 does its own stuff there. I wouldn't explain that without my lawyer present. I wouldn't talk about G1 without my lawyer present, yeah. I mean, something is wrong there, obviously. The details, maybe Kirk knows better. I know. All right, so if you look at, you're not my lawyer. I'm not talking to you. So this thing is the absence of stop the world all GC. This is the thing that CMS does, right? Parallel does everything stop the world, and this is why the pauses are high. Shenandoah does everything concurrently, so this difference is the absence of the stop the world young GC that is present in CMS, and thus it can achieve the pauses there on the wide range of live data sets. But what about these? These kind of does not look right. And if you talk to the GC guys about this and say, I have a problem and my GC runs into the stop the world events every so often because I have 90% occupancy in the heap, the GC guys would tell you, well, don't do that. Just give yourself larger heap and everything will just work itself out from there. But also be slightly wary when anyone shows you these graphs, because you don't know what the throughput is. It would be easy to have low pauses if you do the 1,000,000 times less work, right? So here are the throughput charts. The throughput, it's not really a throughput chart, it's the operation time. It's the time that you spent doing this workload. And in this particular example, Parallel and Shenandoah has the same operation time, lower the better. CMS is kind of close lead there. What G1 does is interesting. And if you look at the GC pause time as the percent of the total runtime, you will notice that Shenandoah is there at the bottom, at the zeros there, until the heap gets too crowded for Shenandoah to operate well. Okay. We will talk about this not well thing a little bit. And the major assumption that all concurrent GCs have is that concurrent GCs have to collect faster than applications allocate memory. Or, in other words, applications should always see if there is available memory. In practice, this is frequently true. In practice, there's usually a lot of free space in the heap. GC threads are high priority, and so they run faster than application threads. And applications are not only doing the allocations, they also do some real work, which lets us do our stuff. But if you do the industry-grade GC, you have to care about this unhappy path too. And what can you do? You understand that concurrent GC needs this breathing room to succeed, and all your work is then centered around that. So things that help is the aggressive heap expansion. You have to prefer to take more memory when the alternative is stop the world event. And while we are talking about footprint, and this is the part of the Shenandoah story that triggers, I think, most of the folks, is that there is the non-negligible footprint overhead for Shenandoah. The forwarding pointer that you have to have for every single object at all times adds up to the overheads. And it costs you on 64-bit VM like 8 bytes per object, because you store the uncompressed pointer there. The saving grace for you is that that forwarding pointer is allocated in Java heap, which means you can plan for it more accurately. It's not some off-heap data structure which size you cannot predict and eats up on your memory. From the native parts, you have 2 marking bitmaps. It's an open question whether you can dispense with just one. Every bitmap kind of coarsely describes the heap, describes what objects are marked in heap, and it takes around 1/64 of the heap there. So if you say use Shenandoah GC XMX 100 gigabytes, that usually means that around 95 gigabytes are accessible to Java objects there, meaning you can cram this much of the usual Java objects that you can cram with other collectors. And if you look at the resident set size for the Java process and you will try to see that, you will see that the RSS for that kind of heap is 103 gigabytes, because those 3 gigabytes are basically marking bitmaps, and forwarding pointers are accounted into the Java heap, which simplifies deployment. But all of that is completely dwarfed by the way the GCs size the heap. And to illustrate that point, I have the microservice example. Microservices are cool, right? So Wildfly, Swarm, REST HTTP example, which you feed with the HTTP requests there. It's instructive to look at the kind of time evolution of this workload when it performs different phases. So once you start the application, it does some initial allocations, and right there you can see that Shenandoah is kind of already higher than every other collector. And this is why other collectors have did some young GC poses there already. And Shenandoah didn't. It just preferred to expand the heap rather than doing the GC cycle. But after you hit the idle phase, the RSS for Shenandoah actually fall down, because Shenandoah can asynchronously uncommit parts of the heap and also do periodic GCs, which we'll talk about a bit later. And under the load, you might see probably the same kind of graph, right? Under load, every GC should decide whether to start GC or expand the heap. Different GCs decide differently. Shenandoah just blankly say, we will expand the heap until we can. J1 is kind of in the middle. If you will change the XMS in XMX values, J1 would kind of stabilize at different levels. Trying to guess where it would stabilize is the adventure on its own. After the application is idle, you can do this. You can uncommit parts of the heap. And the critical realization that you have once you have a concurrent GC is that in OpenJDK, most of the GCs, the GC events are allocation triggered, meaning that it will start GC after a particular amount of garbage have been allocated, objects have been allocated, probably most of that garbage. And so if your application stopped abruptly before you reach that allocation threshold, that means your heap is now full of garbage that you cannot collect because you're barely not there for the GC cycle. Now, you can do a periodic GC, but if you have the step the world GC, that means you're risking the actual large pauses for the application. If you have a concurrent GC, you can actually do the periodic GC, right? So in this graph, for example, this is the first uncommit of the memory, the first uncommit of the memory that we don't need. The second one is the periodic GC, which knocks out the floating garbage that was left around there, and so it falls there to the bottom, right? And so this is basically the Shenandoah's MO. We will take all the memory when we need it. If you tell us XMX 8 gigabytes, we will use all 8 gigabytes when we need it. But we will also give it back when we don't. And we will provide you with the tuning options of periodic GCs and uncommit delays that kind of help you to tune it up. The second thing that you can do in GC is the immediate garbage shortcuts. And to understand how it works, it's instructive to see some of these cycles. So for instance, you have the 100 gigabyte heap. You marked it, but you realize that everything in that heap is dead because it's the young GC workload. And the mark is fast that way because it only visits the alive objects. Then you realize that in some of the regions that you now have no alive objects whatsoever. You don't need to process those regions anymore. You just recycle them right away. And after you recycle, you realize that you have reclaimed like 95% of the old heap. And you just shortcut because why bother continuing the cycle? You already have the biggest bang there. Amusingly, on many workloads that are not having too much things in the old generation, this greatly approximates the generational young GC. because it's very, very, very fast, knocks out the space very efficiently. Partial collections. The central dogma for partial collections in the GC theory is that you want to get average pause times lower by segregating the heap by some property. The usual property is object age, and when you do the separation by age, you get a generational GC. The pesky little detail about this is that it requires, collecting the subheap requires knowing all the incoming pointers to that heap. Otherwise, you corrupt the heap. And different GCs does that differently. If you have the serial or parallel, it has two regions separated, heap separated into generations. And how do you track the pointers? You have the card table, which spans the old generations. When you do the store, you say, OK, if that's a pointer from old to young, I have to flip the card in the card table, saying that that part of the old is dirty. And then, after when I collect the young generation, I have to scan that small part of old generation, looking for the incoming pointers and looking for the places where I have to fix up after the young collection happened. J1 does it a little bit differently. It has remembered sets. Well, card table is technically the part of the remembered sets. And if you do the same trick as in parallel, so you have the card table and flip the dirty card there and say that, when you collect something, you have to track which part of the heap are dirty. It doesn't say anything about that particular region specifically. It says that some area of the heap is dirty. And so there's another thing that is more fine-grained remembered sets that are basically telling you for each particular regions which dirty parts of the heap you have to scan. So in this example, if I collect the first region, I have to also look into that dirty part of the fourth region there. Now, the trouble with that is that remember sets in J1 could get pretty large. Christine tells the anecdote that when the first prototype they did for J1, they executed it on some application, and they realized that remember sets are actually greater than the Java heap itself, which is not cool for the GC. And the most of the engineering work in J1 was focused on getting the remember set sizes under control. And they are succeeded with it, but there are peculiarities. For instance, you can make J1 generational. You can say that some regions are young, you designate them as young, and you can then collect them all at once. That means you do not have to track the references between those regions. And that's probably where the most writes are happening anyway. But there's trouble. If you do a very large young gen, that means your lowest pause goes up because you have to collect all these young regions at once. You cannot collect every single of them. And if you, if you have a very narrow young there, the remember set footprint kills you. When you have concurrent GC, the things kind of change because you can make a coarse-grained card table like in Perl there, but for each particular region. So if I have the store, I can actually say that for this particular first region, I know that the incoming pointer are from the fourth region, and so when I collect the first region, I have to scan through the fourth one. When I have the concurrent GC, I can afford to do this. It's not the pause. It's thankfully I would not scan the whole heap, so this is that. And this is basically the trade-off basically about GC efficiency. So we are trading the full concurrent mark of the entire heap to knowing something about the heap through this connection data and do the simple one. And this is the partial collection. The special case of this collection is generational, even though it should not, even though generational, you can do more advanced things. So observations. Maintaining this connectivity data means more barriers. Every generational GC has barriers that maintain this card table or something else. And that means that you have to make sure that increased GC efficiency covers that throughput overhead. In our Shenandoah example, we identified that not all of the workloads are doing that. In many workloads, it's cheaper to do the full GC scan instead of doing this partial thing. And so it's optional. You can turn it off, turn it on. It is opt-in in current code. so you don't have to pay for partial collections when they don't help. And also, advanced things are possible there. In conclusion, in the single picture, universal GC does not exist. You have either low latency or high throughput, or low memory footprint. You can kind of get low latency and high throughput if you use, say, epsilon, right? But you have to plan for the terabytes of heap then. So if you want to do more work concurrently with the application, that means you have to coordinate with the application, which means more barriers, which means throughput overheads. So for your application, you have to decide which GC you want to use, or whether your current GC is tunable for that. In paragraphs, no GC could detect what trade-offs you're after, either it's latency or throughput. You have to tell it yourself. Stop-the-world GCs would beat other GCs in efficiency throughput-wise. So if you have this workload, then parallel is probably your choice. Concurrent Mark solves the first part of the puzzle, Concurrent Mark. And J1 is already ready for this. You can use it. It works fine. If you want the ultimate latency numbers, then you have to solve copy and compact. This is where Shenandoah comes in. In conclusion, releases, we have this wiki page which lists all the things that you need to know about Shenandoah. We currently develop for JDK 10, but we also maintain the backports to JDK 9 and 8U. And JDK 8U ships in RHEL 7.4 and Fedora 24, and derivatives from RHEL, which include CentOS, quite amusingly Oracle Linux, Amazon Linux, etc. Or you can just, if you want to live dangerously, you can just use nightly development builds. Bug reports are appreciated, success stories are appreciated, failure stories are appreciated even more. So try to use it. It's there, it's runnable. If you run Fedora on your laptop, you can probably run it right now. That's all for now. Thank you. Questions? Right? Yes, Kirk. Do you have a question? Or can you do the question and then you can do the observation?
Okay, then why is the young variable, the young generational pause time tied to the size of young gen?
Because you have to collect the young gen from the start.
But the weak generational hypothesis, the amount of live data in young will be constant.
Well, yes.
Over time, and the cost of the collection is now dominated by the number of live objects.
Yeah. If you believe in generational hypothesis, that's true, but you can make a mistake, and then you have trouble. You can have the workload, and you will have the workload, and there are workloads in which you allocate what you think is young objects, but then you retain all of them. And yeah, I believe that what you're saying is generally true. This is the way that GCs actually exploit the generational hypothesis. The trouble is, it's not always true.
Okay, we can talk later.
Could you please show the previous slide?
Yeah, this one?
No, 69.
69. This one, no? 16. Okay. Yeah. Oh, okay. The slides would be posted. Oh, come on. All right. Questions? More questions? Yeah, Mario.
It makes sense. Thank you.
Oh.
If you want a very low latency, it makes sense to use both a pattern like the disruptor and Shenandoah, or one exclude the other, and if so, in which case you will go with one or the other?
One thing does not exclude the other. If you have the garbage-free application, then you're probably not having a GC collection problem, in which case the choice of GC is probably the choice of the GC barriers, and which place, weirdly enough, you are probably better off with stop-the-world GC, or no GC at all, for that matter. But that's an exception rather than the rule. Most applications do allocate and do need collection every once in a while. So at that point, it's better to have that collection concurrent rather than stop the world, so it doesn't surprise you. No. Do that in mic, yeah. And that's the last question, unfortunately. Yeah.
How does it compare to ZGC, the new
We don't
vehicle?
know. There's no code for ZGC yet.
There is no?
No. Yeah. It does exist, but it's not in open source. We cannot see it. So let's see what it does when it's here.
Okay, so there was no comparison at the moment.
There's no comparison at the moment, yes. And it would not be, I guess, in the upcoming few months until both teams kind of see what's there in both GCs.
And C4?
We didn't compare with C4 for a multitude of reasons. If you want, do it and let us know. All right, that's it. Thank you.